Download this code from codegive.com, link in the description below. The $300 million Typo, a deep dive into Knight Capital's trading disaster. This tutorial explores a real-world example of a catastrophic coding error, the $300 million typo that crippled Knight Capital Group in 2012. We'll break down the incident, examine the underlying causes, and extract valuable lessons for developers to prevent similar disasters. The scene: Knight Capital and high-frequency trading, HFT. Before diving into the specifics, let's establish the context. Knight Capital Group *, one of the largest market makers in the U.S. equity markets. They facilitated trading by matching buy and sell orders for their clients and earning a small spread on the transactions. High-frequency trading, HFT firms utilize sophisticated algorithms and powerful computers to execute trades at extremely high speeds, milliseconds or even microseconds. They thrive on exploiting small price discrepancies and market inefficiencies. Market makers' role: market makers like Knight Capital are vital for market liquidity. They ensure that there are always buyers and sellers available, reducing volatility and facilitating smoother trading. In 2012, Knight Capital was a major player, handling approximately 17% of all U.S. equity trades. They relied heavily on their internal trading platform, known as SMARS, Smart Market Access Routing System, to efficiently process and execute orders. 2. The fatal flaw: the power peg feature. The incident centered around a feature called power peg. Here's a simplified explanation. Purpose: power peg was designed to allow Knight Capital to participate in the NYSE's Retail Liquidity Program, RLP. This program aimed to provide better execution prices for retail investors. Functionality: simplified. When a retail order came in through the RLP, Knight Capital's system would quickly analyze the order and determine if it could provide a better price than the current market quote. If it could, the system would generate and send an order to the NYSE to execute the trade at the improved price. Essentially, it was designed to peg Knight's price to the best available price for the retail order. Implementation: the power peg functionality was implemented using a piece of code. Let's call it power_peg.exe for simplicity. 3. The deployment blunder: a patchwork of versions. Here's where things went horribly wrong. Knight Capital was in the process of decommissioning the old power peg functionality but failed to completely remove it from all their servers. The old code *, an older version of power_peg.exe still existed on several of Knight Capital's trading servers. This old version was no longer actively used but remained dormant. Crucially, it was activated by the deployment error. The new code *, a newer version of power_peg.exe, with a slightly modified version, was designed to replace the old one. The deployment process partially succeeded. On some servers, the new code was installed. On other servers, the old code remained. Worse, even on the servers that had the new code, the old code was inadvertently left active. 4. The $300 million typo: a deeper look at the bug, hypothetical example. Now, let's create a simplified code example to illustrate a plausible cause of the disaster. This is a hypothetical reconstruction based on publicly available information. Let's imagine that the old version of power_peg.exe had a critical bug in how it calculated the quantity of shares to trade. In the new version, this bug was fixed, perhaps by introducing the scale_ factor. Let's see what the fix might look like. Explanation of the bug *. The key problem in the old_power_peg.py example is the missing scale_factor. The function incorrectly calculates the quantity to trade. Instead of trading a small, controlled quantity based on the price difference, it attempts to trade a quantity equal to the price difference. Because the type of the quantity is int, the truncation to an int resulted in quantity being 0. Important note: the code provided here is a highly simplified representation for illustration purposes. The actual algorithm used by Knight Capital was far more complex. The specific nature of the typo and the exact formula are not publicly available. However, the effect was similar: the system was generating excessively large orders. The avalanche of orders, chaos unleashed. With the old version of power_peg.exe running amok on some servers, triggered by the NYSE's opening on August 1, 2012, the following happened. 1. Retail orders arrive. Retail orders began to flow through the NYSE's RLP system. 2. Faulty calculation. The bug in the old power_peg.exe calculated vastly inflated trade quantities. In our example, it tries to buy or sell amounts much larger than it should. 3. Order flooding. The system sent a massive flood of buy orders into the market. Because the quantity calculation was flawed, the orders were for far too many shares and at disadvantageous prices. 4. Price distortion. The excessive buying pressure caused the prices of numerous stocks to swing wildly out of control. 5. Automatic execution. Knight Capital's system automatically executed these erroneous orders. 6. Massive losses. Knight Capital was forced to buy back the stocks at inflated prices to cover the trades it had made, resulting in staggering losses. 6. The aftermath: bankruptcy and acquisition. Within 45 minutes, Knight Capital had lost $440 million. The company was on the brink of bankruptcy. They were forced to seek an emergency bailout and were subsequently acquired by another firm. The $300 million loss figure is the pre-tax loss after offsetting some trading gains. 7. Lessons learned: preventing coding disasters. The Knight Capital incident offers crucial lessons for developers and organizations involved in critical systems, especially in finance. 1. Robust deployment procedures. Formal checklists. Implement detailed checklists to ensure that every step of the deployment process is followed correctly. Rollback plans. Have well-defined rollback plans in place to quickly revert to a previous stable version if problems arise during deployment. Automated deployment. Automate as much of the deployment process as possible to reduce the risk of human error. However, carefully test the automated deployment process itself. Verification. Ensure a thorough verification process after deployment. Verify critical components are running with the correct versions. 2. Thorough testing. Unit tests. Write comprehensive unit tests to verify the correctness of individual code components. Integration tests. Test how different parts of the system interact with each other. Stress tests. Subject the system to high loads and extreme conditions to identify performance bottlenecks and potential vulnerabilities. Regression tests. Run regression tests after any code changes to ensure that existing functionality is not broken. Simulated environments. Create realistic simulation environments to test the system under various market conditions before deploying to a live environment. 3. Code review. Peer review. Have multiple developers review code changes to catch errors, improve code quality, and ensure adherence to coding standards. Automated code analysis. Use static analysis tools to automatically detect potential bugs, security vulnerabilities, and style violations. 4. Circuit breakers asterisk. Asterisk implement circuit breakers asterisk design systems with circuit breakers that can automatically shut down or limit the impact of faulty components. For example, if a trading algorithm starts generating abnormal orders, the circuit breaker can halt trading to prevent further losses. Asterisk thresholds and monitoring asterisk set up monitoring systems with predefined thresholds to detect unusual behavior. 5. Version control and configuration management asterisk. Asterisk centralized version control asterisk use a centralized version control system, example Git, to track all code changes and configurations. Asterisk configuration management asterisk use configuration management tools to automate the deployment and management of software configurations across different environments. 6. Dependency management asterisk explicitly manage dependencies between different software components to prevent compatibility issues. Use tools to track and manage dependencies, example Maven, npm, pip. 7. Clear communication asterisk. Asterisk open communication channels asterisk foster open communication channels between developers, operations teams, and business stakeholders. Asterisk incident response plan asterisk have a well-defined incident response plan in place to quickly address and resolve any issues that arise in production. 8. Post-mortem analysis asterisk. Asterisk conduct a thorough post-mortem analysis after any incident to identify the root causes, lessons learned, and actions needed to prevent similar incidents in the future. 8. Code example, implementing a basic circuit breaker, Python. Here's a simple example of a circuit breaker pattern in Python. Explanation of the circuit breaker asterisk. Asterisk states asterisk the circuit breaker has 3 states. Asterisk closed, the service is operating normally. Asterisk open, the service is unavailable due to repeated failures. Calls are blocked. Asterisk half underscore open, a test call is allowed to see if the service has recovered. Asterisk failure underscore threshold asterisk the number of consecutive failures before the circuit breaker trips to the open state. Asterisk reset underscore timeout asterisk the amount of time the circuit breaker remains in the open state before transitioning to half underscore open. Asterisk call, func, asterisk args, quargs, asterisk this method wraps the call to the target function. It checks the current state of the circuit breaker and either calls the function, raises an exception, if the circuit is open, or allows a test call, if the circuit is half open. It also handles updating the circuit breaker state based on the success or failure of the call. 9. Conclusion, the importance of rigor and vigilance. The $300 million typo at night capital serves as a stark reminder of the potential consequences of coding errors and flawed deployment procedures. In high-stakes environments like financial markets, even seemingly minor bugs can have devastating effects. By implementing robust development practices, thorough testing, and appropriate safeguards, organizations can significantly reduce the risk of similar disasters and protect themselves from catastrophic financial losses. The key takeaways are to embrace a culture of rigorous testing, automation, and continuous improvement. The vigilance and care taken in developing and deploying code directly translate to the stability and reliability of the systems upon which the modern financial world relies.